Um, Good morning, everybody. I'm Dingbo from National University of Defense Technology, China. It's a great pleasure to have this opportunity to talk about cloud-enabled robotic collective intelligence here. My presentation can be divided into three parts. Yes. Firstly, I'll give a brief introduction of the concept of robotic collective intelligence and discuss why cloud is necessary in many cases. And secondly, we will give an in-depth discussion about the roles of cloud in collective intelligence. We'll talk about some well-known research works in this part as well. Finally, I will briefly introduce challenges in this promising field, as well as some of our initial practices. The first question is, what is collective intelligence? According to Wikipedia, collective intelligence is shared or group intelligence that emerges from the collaboration, collective efforts, and computation of many individuals and appears in consensus decision making. It strongly contributes to the shift of knowledge and power from the individual to the collective. This concept is originated in 18th centuries with Marcus de Condor. Sorry for my French pronunciation. He is a French philosopher, mathematician, and early political scientist. His jury theorem states that if each member of a group to vote, if each member of a voting group is likely to make a correct decision, the probability that the highest vote of the group is a correct decision increases with the number of the members in this group. It is a typical example of collective intelligence. Okay, the term collective intelligence originally appears only in social biology, political science, and other social fields. However, today we will talk about robotic collective intelligence, or collective intelligence in robotics. Following the original definition of collective intelligence, we can define the robotic collective intelligence as the intelligence emerges from the collaboration, collective efforts, or computation of many autonomous robots aiming at fulfill a task or a group of tasks. There are many driving forces which of such kind of collective intelligence, such as the complexity in the problem domain, which is beyond the capability of a single robot, and the flexibility, reliability, and efficiency brought by the distribution of robots, and the intelligence emerged from nonlinear interaction among the robots, and also making aware of the intelligence from human society and other entities. Also, this concept, the robotic collective intelligence, is a coined new concept. There are already many works existing research towards this goal in recent years, such as general multi-robot systems, which usually consists of several highly autonomous and complex robots, and the robot swarm, which consists of thousands, hundreds, or even thousands of mostly simple, physical robots, and the cloud plus multiple robots, which we will talk today. Okay, let's take a look for some examples of robotic collective intelligence. This is a video from Artificial Intelligence Lab VUB. It is an early work conducted about 10 years ago. We can observe some interesting phenomena focused on robotic collective intelligence in this video. The robot coordinated to drag a group of objects. While a single robot finds that it cannot cross a slope, a UAV will take off and evaluate the situation. It observes and then makes some plans and then choose some robots to do some special actions. We can see from the video, and then you can see that the robots will connect connect with each other and cross the slope cooperatively. Another video is from the Harvard University, which has been published in Science in 2014 and has also been listed as one of the top 10 scientific achievements of the year by the Science magazine. In this video, thousands of simple low-cost robots are used. These robots can be programmed and communicate with each other. This work demonstrates self-assembly of complex two-dimensional shapes with such a 1,000 robot swarm. In nature, groups of thousands, millions, or trillions of individual elements can self-assemble into a wide variety of forms purely through local interaction. This work imitates this phenomenon in the nature. Okay, go back to today's topic. Since existing works without code have been done so well, why do we need code in robotic collective intelligence? Before answering this question, let's take a look at a real-life problem in robotics, that is robot grasping. This is a typical and perpetual problem in robotics. I use the term perpetual here because many people believe that we do not touch the essence of human grasping yet, not to mention imitating it in robotics. Human grasping is a seemingly simple but actually quite complex. Human grasping is a very complex behavior. It involves a lot of sensing, intentional and subliminal decision, and delicate action. Major research methodology in robotics is still based on the observation, modeling, planning, and action sequence. For example, the robot can predict the center of gravity of an object by observing its shape, and then it can calculate an appropriate right way to grasp it. However, this method is only suitable for very simple objects and scenarios. It is still far away from real-life applications right now. Recently, the rapid development of computing technology offers a new hope to address this challenge. Let's take a look at two recent research works. The first work is a Medium Object Challenge initiated by the Brown University recently. It tries to address the grasping problem through another way. The robots need a great deal of knowledge, in particular, the models of various objects in robust grasping. More models, more powerful the robot is. However, in practice, a robot can only learn a limited set of object models. Therefore, can we accumulate a huge knowledge repository on the cloud, and the robot can access it in an on-demand style? The Medium Object Challenge tries to encourage the robots all over the world to contribute to this goal and enable the knowledge sharing between robots with the aid of a background cloud. As it stated in its work page, if we had over 300 research vectors, vector is a model of robot working, we could reach our goal of 1 million objects in just 11 days. This work has been listed as an example of robots that teach each other, one of the 10 breakthrough technologies in 2016, named by the MIT Technology Review. The second one is the Google hand-eye coordination experiment in April 2016. As I have mentioned, traditional research is based on the observation, modeling, planning, and action paradigm. The robot have to be built in a lot of knowledge in advance. However, Google believes that robots can learn how to grasp objects itself, just like human children do. We don't need to tell human children how to grasp an object. They just try many times and then suddenly learn how to grasp it. In this experiment, Google uses 14 robotic arms and allows them to grasp objects in the basket in front of them without any prior knowledge. Those robots can use cameras to observe the target objects as well as the effects of their own actions. That's why this experiment is called hand-eye coordination experiment. The data is used to train a back-end neural network in the cloud, as shown in the left graph. After almost 1 million attempts, they found that the robot successfully learned how to grasp different objects, including objects that are large, small, hard, soft, deformable, and translucent. The robots also learn how to correct mistakes in real time. Note that in this experiment, all knowledge is learned by data collected in the robot's trial and error process. The cloud computing infrastructure acts as a common brain in the backend. Okay, why do we need a cloud? In short, the reason can be concluded by the words in a technical report published in this month, named A Back Review of Systems Challenges for Artificial Intelligence. It states that AI systems deployed at the edge, such as self-driving cars, drones, and home robots, are increasingly sharing data and leverage the computational resources available in the cloud to update models and policies. We all know that the famous report, A Back Review on Cloud Computing, which has been almost a Bible in the cloud computing field. They hope this report can also be a Bible in artificial intelligence, especially in system-level challenges or artificial intelligence system construction. The expression in Beckley's report is too high level and too ambiguous. In this talk, I'd like to answer the question, why do we need a cloud, from 3 dimensions: collective coordination support, collective intelligence evolution support, and hybrid collective intelligence support. It is also the roles of cloud in robotic collective intelligence in our view. I will interpret each dimension in depth one by one in the following slides. Okay, the second part of my presentation, how does cloud contribute to robotic collective intelligence? Firstly, since coordination is a direct representation of intelligence, cloud can provide support for robotic collective coordination. Cloud promotes collective coordination mainly in two ways. Firstly, in a robot collective system, each individual robot has only a local view of the world. However, to facilitate collective coordination, a global view or a collective view is preferred in many cases. The cloud can act as an infrastructure for such kind of collective cognition. As shown in this graph, it can collect individual perception data, aggregating this data to form a high level of global view. Secondly, the cloud can act as an oracle based on this high-level view. What I'd like to emphasize here is that it is different from traditional centralized controller model. The cloud should not be a controller. Enforcing stringent control from the cloud to autonomous robots is not only impossible but also unacceptable. In a cloud-enabled collective system, the cloud should act as an orchestrator instead of a controller. Its role can be analogous to that of a government in a market economy. However, it is of great challenge in realization, especially in substantiating this style to make it computable. I will talk about the action orchestration at the end of this presentation as a future challenge. We'll talk about the first part, the collective cognition, by an example in the following several slides. A typical case of collective cognition is multi-robot SLAM. As we know, SLAM, or simultaneous location and mapping, is a very classic problem in robotics. It constructs the map of the environment accumulatively, while simultaneously locates the robot itself, just like the action when a person who enters an unknown environment. Multi-robot SLAM involves a team of robots cooperate to map an unknown environment, which is a foundation for many multi-robot tasks, such as disaster rescue, patrolling, and searching. A common way to realize multi-robot SLAM, as shown in this figure, is that each robot build its own map continuously, and then maps are being merged by a master node periodically. The merging process involves map alignment, map fusion, and global optimization, which use cross-robot data to eliminate errors. This process involves highly complex and iterated computation. And since this process can be operated in a best effort model, it is ideal to be placed on the cloud. We can leverage cloud resources to accelerate this process and promote the global optimization efficiency with the aid of the rich resources on the cloud. A well-known work towards this goal is a cloud-based collaborative real-time 3D mapping experiment conducted by ETH Zurich. It uses two low-cost robots. They assembled themselves in Switzerland to collect 3D image data. An Amazon data center in Ireland is used to carry out computation tasks in the backend. In addition to general uploading of each individual robot's computation, as shown in the left figures, some backend entities on the cloud is responsible for optimizing and merging the map from two robots. Based on this architecture, they successfully realized collaborative real-time 3D mapping, which is originally being regarded as mission impossible on such kind of low-cost robots. Recently, our team has also made some progress. in cloud-supported collective SLAM. I'll introduce them briefly. The first one is a parallelized multi-robot SLAM framework. We can foresee that hundreds of robots will cooperate to finish a task in the future. Thus, in this work, we enabled the complex computation in collective SLAM process, that is map alignment, map merging, and optimization to make avail of the parallelized resources on the cloud, such as a large number of servers in a cluster. More servers, more robots can be supported in a collective SLAM process. In our simulated environment, we can support up to 256 robots, real-time mapping, merging, and optimization with 16 servers in a simulated environment. This experiment is conducted on the Aliyun Cloud, a famous cloud computing provider in China. This result is one order of magnitude higher than existing work, which can only utilize a single server in the map merging process. Another work we conducted is cloud-supported relocalization in multi-robot SLAM. Relocalization can be regarded as an optimization means in SLAM. When a SLAM process failed, such as the tracking stage does not output the right results in time, or the robot has been kidnapped. I know that Zhang is Zhang's project. Yes. A robot will try its best to determine its location and thus avoid to start the SLAM process from scratch. It is usually realized by highly computation-intensive algorithms, such as appearance-based merging with historical keyframes. When we migrating this process to the cloud, we can at least get two benefits. Firstly, the history data can be shared among robots, which increase the probability of success in relocalization process significantly. And secondly, we can utilizing cloud resources to expand the search scope, the search depth. The robot's computation power will not be a bottleneck. However, this process is also of great challenge and need elaborate design. If you are interested in our approach, you can refer to the paper we have been published on ACA conference. This work has been published. The first work has just submitted to a conference. Okay, the second role of a cloud is to support the collective intelligence evolution. The first question is, what is collective intelligence evolution? The prospect foreseen by Stanford's report on AI and life in 2030, the 100-year study on artificial intelligence, can illustrate this concept. It takes home robots as an example and says that cloud is going to enable robots sharing of data sets gathered in many different homes, and then power improvements to already deployed robots. As a result, the collective of all home robots as a whole will be more and more intelligent over time. This is similar to human society, whose cultural development is based on knowledge accumulation, sharing, and discovery based on shared knowledge, just like what our researchers are doing now. Thus, robotic collective system should be a growing system too, which can learn and accumulate knowledge from past experiences as a whole. They can evolve to cope with open environments and complex tasks. This scope can be divided in two levels. The basic level is the individual knowledge sharing, aggregating knowledge each individual accumulated, and sharing among individuals in a well-defined way. And the higher level is collective knowledge discovery, including discovering knowledge on the collective level. The knowledge only can be found on the collective level, and this knowledge can contribute to both individual and collective decision. Okay, a well-known example is Robotic, and I believe everyone know it. The aim of Robotic is to use the internet to create a giant open source network database that can accessed and continuously updated by robots around the world, just as stated in the robots webpage. What if robots could learn from the past experience? And what if they could share the newfound knowledge instantaneously with their peers? However, today I'd like to talk about another trend, hot sports in robotics, that is deep learning, or multi-robot deep learning. The second example is cloud-supported multi-robot deep learning, just as the Google hand-eye coordination experiment I introduced at the beginning of this talk. As we know, deep learning is very hot right now. In contrast with traditional machine learning algorithms, it provides a general-purpose learning procedure so that high-quality features can be learned autonomously and efficiently from data instead of the handcrafted features. Besides, it provides multi-level abstraction by hidden layers, which can model complex non-linear relationships. What I'd like to lay emphasis on is that deep learning and cloud computing are naturally related. Why do we say that? The basic idea that software can simulate the large area of neurons in an artificial neural network is decades old, and it has led to as many experiments as breakthroughs. But just as the Nobel Prize winner and physicist Philip Edison says, more is different. Because of improvements in increasingly powerful computers or cloud computing infrastructures, and more data collected by the development of internet and cloud computing, computer scientists can now model many more layers of virtual neurons than ever before. The advancement in data and computing power is two major driving forces of today's deep learning technology, and these two aspects are highly related to cloud computing. As regarding robotics, although the view on deep learning in robotic community is not an optimistic area in concrete before 2050. However, currently it has been widely accepted by roboticists. Basically, deep learning can contribute to robotics in two dimensions: perception and control. Perception is a traditional area of strength of deep learning. Its tasks are usually featured by classification, such as object recognition, understanding the semantics of the environment, etc. Recently, some novel deep learning algorithms also emerged to contribute to the control of robots. The most famous one is deep reinforcement learning, which lets the robot can learn actions policies from trial and error experience. It is also the foundation of AlphaGo. However, why cloud plus multiple robots? We believe that there are at least the following four benefits. At the most basic level, if we place the models learned by each robot onto the cloud, we can enable the knowledge sharing among robots, since the deep learning model is a typical concentration of knowledge. Secondly, a prominent difference of robot learning and traditional machine learning is that many robot training data have to be collected in the interaction with the physical world, which is costly and time-consuming. By collecting data from multiple robots, the training speed can be significantly accelerated. On the second level, since the physical world is full of noise and full of variety, full of a lot of variety, learning from the data collected from multiple robots can enhance the generalization ability of the model. And more importantly, the cloud plus multiple robots deep learning architecture can discover knowledge only which can be found on the collective level. Okay, an example. This is the work based on the Google's hand-eye coordination work. It published in the last November on Google Research blog. It is titled as How Robots Can Acquire New Skills from the Shared Experience, as stated in this blog. However, robots can instantaneously transmit the experience to other robots over the network, sometimes known as cloud robotics, and it is an ability that can let them learn from each other. This blog involves 4 papers, which covers learning motion skills directly from experience, learning internal models of physics, learning skills with human assistance, and these papers published on 3 published on ICRA 2017 and 1 on IROS 17. Okay, the last role in of cloud in collective intelligence, the hybrid collective intelligence. Here, the hybrid means 2 types of hybrid. First, the robots plus existing information systems, and secondly, the human in loop. Here, we collective is a more broad sense one. It means not only robots, but also other entities in the world, such as existing information systems, such as human and organization and other things. For robots plus existing information systems, cloud acts as a bridge between cloud and existing between robots and existing information systems. And for human in loop, cloud can also act as a portal between them. In this scenario, human can be an oracle which guides the robot's action or upgrade them by software evolution and other types, or human as a call center. When the robots confronted with a problem it cannot solve, it can call the human to help. And the human as robot's partner, or human as a learning target. Human intelligence can be, the robots can learn from human intelligence. Okay, an example as well. This is Robot Hub, a 4-year European project that started in 2012. It demonstrates Wikipedia how to teach Wikipedia and human how to teach robots. We can see that it learns from the Wikipedia, and the instructions are combined from video and other demonstration given by humans, and from human teaching hand to hand. And these information sources are combined. And then the robot learn how to cook. We can see that. Okay, it's just a very short video.
It's not easy.
Okay, the last part of my presentation we'll talk about some challenges and some initial practices. Cloud-enabled robotic collective intelligence is a very young field. Most well-known work is conducted in recent 3 to 5 years. The research challenges are also developing rapidly with cloud, robotics, and AI technology. I list some challenges here, which is far from complete. However, I hope that they can inspire those who are interested in this promising field. The first one aspect is on the general system level. A cloud-enabled robotic collective system will involve a lot of robots and cloud computing entities. How to deal with heterogeneity and interoperation among them is a great challenge. For example, a dynamics model learned by a robot may be not applicable to another robot since the hardware are different. And the interoperation on the semantic level of both robotic data and robot behavior should be considered, especially while different robots are following different technical systems today. And since robots directly manipulate the physical world, constraints in the physical world will be mapped into robotic software in the form of quality of service, such as response time, priority, and reliability. However, while we adding the remote cloud into a robot system, the introduction of uncertainty, such as unpredictable network latency, is inevitable. This situation gets worse, while many services on the internet, and even the internet itself, are designed based on the best effort model. Thirdly, an important lesson learned from existing practices is that complex distributed computing system with no cloud plus multiple robots is a typical distributed computing system. Such kind of system should not be built totally from scratch. We have to provide reusable infrastructure supporting robotic collective systems. The second aspect is about the support of collective coordination. As we have mentioned, the cloud in a robotic collective system should not be a controller, but an orchestrator. Its role can be analogous to that of a government in a market economy. This is very challenging and need a delicate trade-off between centralization and distribution or decentralization. Another challenge in this aspect is task-specific collective perception and orchestration algorithms. And for large-scale collectives, it is difficult to engineer everything. We may have to learn from complex systems and introduce related techniques such as mechanism design and conflict resolution among behavior emergence and rule-guided emergent behavior. The cloud provides an ideal base for substantiating these techniques. The third aspect is about collective intelligence evolution, including the well-defined approach to represent and share robotic knowledge. The collective learning algorithms with the aid of the cloud, and the incremental learning method with training data collected from the physical world instead of predefined training data sets. And for the last aspect, the hybrid collective intelligence. The first challenge is that we need more comprehensive understanding of hybrid, including the roles of legacy information systems, human and other entities, and the characteristics, and how can we combine them together. We must cope with the interoperation between robots and existing information systems, not only on the syntax level, but also on the semantic level. And for human-in-loop hybrid intelligence, we have to deal with the challenge that how to incorporate human behavior models into robotic systems. For example, human computation, such as Amazon Mechanical Turk, can provide support when the robot's request is beyond the cloud capability. However, the cost of human intervention with the cost of robot failure should be cautiously balanced. Okay, the last several slides will quickly overview our initial practices towards cloud-enabled robot collective intelligence. Our work can be divided in two parts. The QoS over reusable software infrastructure and the task-specific collective perception and orchestration algorithms. For the later, we have done some work about collective SLAM, trail following, path planning. The collective SLAM I have mentioned earlier, and the trail following has been presented yesterday by my student. And I'll focus on the QoS over infrastructure. It's the macros DRT and the cloud join. In order to gain end-to-end QoS and avoid unwanted situations such as priority inversion, each link in the robot network cloud chain should take the QoS property into account in a cloud-enabled robotic collective system. And the specified QoS properties should be propagated and inherited among each link. Only in this way, the system level and end-to-end QoS property can be assured. Aiming at the magic, we can see that it involves the local QoS, the magic QoS, and the service QoS, three aspects. The local QoS on the robots is a mature one. There are many work cope with it. However, the magic QoS and the service QoS are new challenges introduced by cloud robotics. Our first work aims at magic QoS. It is Macros DRT. It is based on it is a software infrastructure focused on real-time and scalable data distribution in robotic distributed systems. Our work is based on ROS, a robot operating system. I believe everyone knows it. Its software package model has been a de facto standard in robot software. However, it did not provide support for real-time message. Our work is a modified kernel of ROS, which integrate a mature real-time standard real-time match standard into ROS kernel, that is DDS, data distribution service for real-time systems. It is a mature real-time message transfer standard proposed by OMG, Object Manager Group. It supports time constraints in message-oriented communication, such as transport priority, latency budget, and other QoS params of a topic. And it is fully compatible with official ROS. I had to lay emphasis on that the recent version of ROS, ROS 2, also adopt DDS as its underlying message transfer standard. However, our work is published before ROS 2. Our work is published in 2014, and our work is fully compatible with Robotic. That is, existing ROS applications need no modification, and it can gain from PDS. This work we have some opinion exchange with OSIF, and they confirm our work and highly appreciate. Yeah. This is some positive feedback from the robotic community, and it is open source. If you are interested, you can download it and try it. The second work is Cloud Droid. That is ROS package as QoS enabled cloud services. We see that there are already thousands of reusable ROS packages. However, they are supposed to run on robots locally or just in a local network, not on the cloud. So only one robot, most of them. For example, a SLAM package can only serve a robot, not multiple robots. The question is, can we directly convert them into cloud services which can serve multiple robots and provide QoS ability in its invocation? This involves the ROS application model, or the transfer from ROS application model to the cloud service model. In ROS application model, it serves single robot and need a lot of manual configuration, such as the ROS master address, and it did not contain distributed QoS. However, in a robotic cloud service, it may be accessed by multiple robot clients, and it should be a black box, a service-oriented interface. You should not configure the ROS master on the cloud. And for robotics cloud service, we should provide some QoS assurance in service invocation. Our answer is Cloud Droid, an ongoing project which is also open source. It is a QoS server, a PaaS, platform as a service platform, supports the direct deployment of ROS packages. It mainly concerns the service QoS. Feature of Cloud Droid. The first feature is it transparently wraps a ROS package into an internet accessible cloud service. It's just an interface. You can access it directly, need no configuration. And then it can automatically generate a service stub on the robot side, which can replace the cloud side ROS package. For example, if your application you use a SLAM package, and you can put the SLAM package onto the cloud and just replace the original package on the robot with the stub automatically generated. It can access the cloud automatically. And the third feature is that it provides QoS guarantees to some extent, certainly, because the environment is uncontrollable during service invocation by the collaboration of client and cloud. This work has been published on IEEE Cloud 2017, and it is also open source on GitHub. If you are interested, you can download it, and we welcome you to contribute it to it, because it is still an ongoing project. Okay. Okay, that's all. Thank you for your attention.
The most interesting part I noticed is when you started to discuss about the potential guarantee of quality of service.
Yeah.
So surely you talk about guarantee of quality in both value and time. Yeah, so you have to guarantee the value returned from cloud is what you expected, and also the results should arrive within the time constraint.
Yeah.
Can you give us an example? So how as applications, how could we get a support from your infrastructure system? I have to define by myself.
You have to define you can define it in two ways. Okay. First way, you can define the priority, just and the infrastructure will schedule the task according to your definition. It provides no guarantee, but
it's more QoS aware. Platform, so that you can at least talk about these things. Okay. Whether in other context you would not be able to talk about. So your system
basically doesn't guarantee, but you probably try your best.
Try my best.
Yes. Best effort.
Okay. Secondly, if you have QoS support on the network level or on the network, you can define the strict deadline.
Yes.
But however, hardware must provide it.
IPv6 provides a QoS layer, so you can rely on the QoS layer of IPv6 to try to.
Yeah, if you have QoS guaranteed protocols at the bottom layer, I can utilize it. This DDS has this ability.
Otherwise, I think you will have to constrain the way applications that are running on the cloud are written, so that you could say that you have guarantees, and the OS, the operating systems or otherwise, would implement those guarantees. But if you need to provide an application that is written in such a way that the system can give it the control when it's time, and then you have a worst case execution time on the application. It's the only way that you can have guarantees in some sense. If the application is not written to provide any guarantees about the time, like you said yesterday, with long tail or things like that, there's no way. So
when we designed our driverless cars at Leeds, we were actually quite nervous about guarantee of time constraints. So we just went for a very conservative approach. So any timely decision we have to make on board. So any driving critical actions. So basically we design software system which is on board on the car itself. So then other actions, particularly including large scale calculations like road planning. So we are assuming even you miss out some results, it's not life-threatening. So we pass such kind of planning task back to the cloud. So at the moment, I understand it's still quite a challenge to build up that guarantee link, between robots and the cloud.
I believe that it is not necessary to provide a strict guarantee of QoS as onboard applications in a cloud robotic systems. We have this is a two-way effort. You should choose the right applications to run on the cloud, and then we can do our best to provide some guarantees or guarantees to some extent. This is we should not expect that a cloud robotic system is with no fault. It's no fault. Or will not failure.
I have not really a question, but a comment or suggestion, or I don't know. But these days I'm more and more amazed by the fact that overall, when we are talking about cloud computing, artificial intelligence, collective intelligence, things like that, nobody seems to care about the resources to do that. Resources to do that. Computing resources.
Computing resources.
Yeah. if we go historically, computers were invented, let's say, in the 40s. In the 60s, they began to spread out. In the 70s, in the 80s, we began to learn about how to use those things that were computers. And essentially, at that time, we were talking about one computer. Okay, what we can do with one computer. And of course, I think that our fellows ancestors were quite excited about what they could compute with computer, and they began to compute, and they saw that some problems were quite hard to solve. And so we saw appearing a computational theory about the difficulty of computing, and we've seen that there were very hard problems that we called NP-complete problems, and we had to say at the time that an NP-complete problem, we could only solve small problems of them using the computer we had at the time. And even though at the time the computers were almost doubling in capacity, computational capacity, memory capacity each 1 year and a half, we were still convinced by the 80s that there were problems that we could only solve small exemplars of the problems because of that. Since almost 10 years now, we are listening at discourse about cloud computing, AI, and things like that, that seems to have an underlying hypothesis that the cloud computing infrastructure in the world is infinite, that we will be able to compute anything we want, and there's no problem. And of course, if we go at the raw level, the bare metal level of this system, today, everybody accepts the idea that we are not really entered in the AI, massive big data analytics world, and yet, in 2010, it was less than 3% of all electricity in the world that was consumed by the IT infrastructure of the world, and today we are between 13 and 15% of all electricity in the world consumed by the IT infrastructure. Half of it is by data centers. To give you an idea, I heard recently that at rush hour for TV in the US, more than 30% of the whole internet capacity in the US is taken by Netflix. Okay? And so I would like to see more in those talks, a challenge that would say another challenge is to be able to guarantee an exponential growth in computational capacity of the cloud worldwide, exponential growth in the memory capacity of this cloud computing infrastructure for several decades, so that we can afford to implement all those fantastic algorithms that will process billions and and whatever you want amount of data and be able to process that, because otherwise it means that every year from now we will have to build 10 nuclear power plants more to be able to feed in the computational infrastructure. Otherwise, we will have to live also under a roof of solar panel everywhere in the world. And maybe we'll have to also put a roof of solar panel over the moon. It's not possible. So at some point, I think that one challenge, because I've never seen that in any paper I've read about big data, that would be a new computational theory at what is the expected capacity of a computational capacity needed to solve a problem. I've never seen that. Okay, everybody is talking about I will do deep learning, processing large amount of data, but I've never seen something saying it's exponential in the number of in the size of the data. I've seen nothing about that. and so that we could then assess whether or not we are able to provide this computational capacity. And so maybe we'll end up saying, if there is no major shift in technology, okay, if we continue to rely on the technology we know today, computers as we know, networks as we know, and the way they are consuming energy and the computational power and memory power they provide, it's impossible. Okay, the big data analytics and then everything, we will just say 5 or 10 years from now, we give up. It's impossible. We cannot. It would be like someone that would have told you in the 19th century, we have invited industry, tomorrow we will build an infinite number of cars. And then we have to say no. We don't have enough industry, don't have enough iron, we don't have to be able to build an infinite number of cars. So it's time that we begin to think about that, because at 15% of all electricity in the world consumed by this infrastructure, I don't think it's fair to say that there's no challenge to provide the computational capacity to implement those things. Okay, and so it would be fun to begin to have these kinds of reflection, because I began myself to teach students at master level about autonomic computing, and my flagship application was energy consumption in data centers. So in 2014, and I was telling the students, it's now consuming, the data center are now consuming between 3 and 5% of the electricity in the world. In 2017, I tell them, it's almost 10%.